Okay, let's see the impact of pole zero cancellation. If the system undergoes the pole zero cancellation, then the system order will be reduced by 1 degree. And however, the root locus will be shown only for the reduced form. Therefore, the impact of cancelled pole zero must be also be considered if you need to satisfy the condition of total internal stability as well. Hello. Let's consider the impact of sampling frequency variation over the digital system. Now, you can easily visualize this closed loop system which has been controlled by using the integral controller G of D, and it has a zero order hold G of H, and the plant that is being controlled is 1 over S plus 1. Okay, the digitalized discretized form of this integral control has been mentioned over here directly, k over 1 minus z inverse 1, that can be simplified and can be written as k into z over z minus 1. Similarly, you can take the z transform of this cascaded form with the g of z, that's equal to the combination of overall integral control as well as the system that is being controlled by this controller, and we have taken the directly the z transform of the overall system. This is telling the z transform of this plant along with the zero order hold, and finally the overall open loop transfer function of this whole system g of z is given by kz over z minus 1 into 1 minus e raised to power minus t divided by z minus e raised to minus t, where t is the sampling time, and according to this question, it's defined by the 0.5 second. So you can also change it further to 1 second or the 2 second according to your condition. Sampling the system at 0.5 second give us the g of z, which is the open loop transfer function for 0.393 divided into k of z divided by z minus 1 into z minus 0.606. There are two poles and one zero. Zeros are located at z is equal to 0, and the two poles are z at equal to 1 and z is equal to 0.606. So arranging it to evaluate it for k, we will transferring it to the closed loop transfer function 1 plus kgh equal to 0, and derivate it with respect to z. We will have these two values of z, that's equal to 0.7788 and z is equal to minus 0.7788. One of them will be telling us for the break in, other one will be for the break out point of the k. Now if you put the value of z into this equation for the evaluation of k, you will be able to find the two values of k, and by putting z is equal to 0.778, you will get k is equal to 0.1244, and for z is equal to minus 0.778, the k is equal to 8.041. From both the value of z's, k is positive, that is been justified from the root locus, and from here it has been justified that at 0.77 this is the break-in point for the value of k is equal to 0.12. that means that we will be residing over this position, and at c is equal to minus 0.778, k is equal to 8.041, that means we will be over here. So this is how we actually sampled our system for 0.5 second. Now if we perform the same steps and increase the sampling time equal to 1 second, you will realize that this diameter of the circle has now been reduced, and the value of k as well as the z's will be changed. So at t is equal to 1, the k is equal to 0.2449, which is the breaking point, and the breakout point is k is equal to 4.083. Similarly, and lastly, if we reduce the t, increase further, t is equal to 2 second, the diameter will be reduced further, and the values for the gain has been changed once again and are now 0.4622, which is the breaking point, which has been reduced further, and the breakout point is now at 2.164. So this is how, by changing the sampling time, you will be able to change the gains for the break-in and breakout point as well. Let's try to study the impact of varying sampling frequency over the transient response. A large sampling frequency has detrimental effects on the relative stability of the system. Now, there is a thumb rule that can be used to understand this impact. The sampling should be 8 to 10 times during the cycle of the damped sinusoidal oscillation if the response is underdamped. The sample should be done at 8 to 10 times during the rise time for overdamped step response system. For any value of S defined for the underdamped system in the upper half, we can demonstrate the relevance for the damping ratio to be as asymmetric with respect to the upper half, and it should be same as that of the lower half as well. For the second order underdamped system, you can easily find out the damping ratio if you are able to utilize the information from the S domain or second order characteristic equation and translate that equation with respect to the z. The magnitude can be calculated as z magnitude is equal to e raised to power minus t zeta omega n, and where omega n is a natural frequency and zeta is the damping ratio and t is the sampling time, and the angle can be easily found out by relating it with the t omega n into 1 minus zeta square whole under root, or the t omega d, which is the damping ratio, and the theta that is being evaluated is in radian. From this structure, point C and D, one can easily find out the information regarding the zeta. Let's try to figure out the impact of changing the sampling time over the transients. Now, if you realize in the three pictures that we have kept the k is equal to 2, however at 0.5 second the number of transients in the output is much more higher as compared to the transient in sampling at the 2 second. Now this shows that if we keep on increasing the sampling time at from 0.5 to the 2 second, the transient will start to die out very rapidly. Here let's try to figure out the static velocity error for the different sampling frequencies, keeping the value of the gain to be fixed at 2. Consider this g of z, which is the open loop transfer function of the system that is being sampled at 0.5 seconds. So the simplified version of this is the 0.787 divided by z minus 1 into z minus 0.606. According to the formulation of the static velocity error is defined by k of v is equal to limit where z approaches to 1 and apply to the 1 minus z raised to power minus 1 into the system g of z divided by the sampling time. Now moving on, we will be able to find out the steady state error at this sample time 0.5 second. Putting the values into this g of z and define the t for the 0.5, you can easily see that the steady state error at this sample time is up to 0.25. Now let's repeat the process for the same system defined by the k is equal to 2 and the sampling time is now replaced by 1. You can easily observe that the velocity error is now equal to 2, and the steady state error has been increased to the 0.5. Similarly, if I increase the sampling time by t is equal to 2 seconds, you can easily visualize by passing through the same series of steps, the steady state error is now equal to 1. That means by increasing the sampling time, the steady state error will also be increased. So that means that you need to imply some other kind of the combination of these controllers like PID that can reduce the error for the given sampling time as well. You can easily see that for the ramp input given to the system, and we can easily find out the velocity error that has been marked for the sampling time 0.5 second to be. Steady state error is now 0.25. Now if we increase the sampling time to the 1 second, the steady state error has also been increased by 0.5, and furtherly increasing the sampling time to 2 seconds, the steady state error has now increased to 1. So I hope so that you have understood the mechanisms of the construction of root locus, and using those procedures how we actually evaluate the controller designed for our system, and the impact of varying the sampling time over the transient, and that of the impact on the gain as well have been demonstrated clearly in this lecture. So I hope so that you have enjoyed it well. So if you have any question, just do comment below, or email me at the address given in this description as well. So have a nice day.